This is 5.5, Systems and Energy Conservation. Today we're going to look at energy on like a whole system and like the total energy and how that energy changes. We'll look at conservation and conservation of energy and the non-conservative systems as well. So basically the same thing that we've been talking about. Is energy conserved? Is energy not conserved? That's where you start. So non-conservative forces. This is like friction. This is like a force that's being applied to the system. So the duct system, the duct table is the system. I am not the system. I'm going to add energy into this, and that as soon as it crosses the boundary into the duct and causes it to move, that would be work on the system. There is energy to be taken out of the system because the duct is moving across the surface, and as it moves across, friction takes out some of the energy. So, and that is transferred into heat. So whenever you have energy taken out, there's work done on the system, and the work is going to be equal to any change in energy, whether it's an addition or a subtraction.
Wait, what does NC stand for?
Not conserved.
Wait, so W stands for work, so it's non-conserved work.
Yes.
Okay.
Stop. Okay, so there are a couple of equations that we have for non-conserved work. Again, I've given this to you yesterday and I think maybe even the day before. Work is going to be equal to the change in kinetic energy plus the change in potential energy. Or if you reorder the stuff, basically it's going to be your final energy, whether it's kinetic or potential, minus your initial energy. So energy can either cross a boundary, for instance, my energy going into the duct to cause it to move, or it can be transformed into some other sort of non-mechanical energy, such as thermal energy. So friction. It's, I mean, if you're looking at the duct table system, as the duct moves across it, friction slows it down, and it's still, the energy is still in the table, but it's not mechanical anymore. It's heat energy. So the table hasn't lost that energy because it's heated up, but it's not really part of our system anymore. Not mechanical system anyways. I prefer the tax better.
Well, it's less tax, more restorative.
No. You want to eat in my classroom, you got to feed me too.
Exactly.
My fourth period, somebody brought me a pretzel. One of those big soft pretzels.
Oh, wow.
Pretty good.
How much you get of that?
Hmm?
How much did you get of that?
She brought me like a whole pencil for pretzel.
Oh.
Yeah. Her friend gave me like a piece of one of her pretzels, and then at the end of class, she was like, "I have extra. You want one?" Okay, so we got all blue cups. We're good. All right, so transferring energy. There's lots of different ways you can transfer energy by work. So you can apply a force. This produces some sort of displacement on the system. Heat. Heat is basically transferring heat by collisions between atoms or molecules. So basically, you put a cold spoon in a cup of coffee, and that coffee molecules because they're high in temperature, they're moving around a lot because they have a lot of extra energy, which is technically kinetic energy because they're moving. But that's not the kind of kinetic energy we're going to talk about with our systems. We'll not tell you a little bit later. So they have a lot of energy. These collisions with the spoon are going to start to move the molecules in the spoon around more, and so that spoon is going to warm up. It's basically taking the energy from that coffee, the hot coffee, to warm up the spoon. That means the coffee is going to cool a little, so its molecules are going to slow down just a bit, and the spoon molecules are going to speed up, making it warmer.
Two questions. First of all, is daily recording just going to be like a thing now?
Yes.
Okay, and second, well, where can we find them?
Trying to upload them to YouTube, but I'm having a hard time because I forgot my phone at home. But eventually, I'll works. Yes.
You know when you eat something that's really hot, and then it's in your mouth, and then you're like, it's hot, 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 and you kind of keep it there and open your mouth for a little bit, then it becomes cool in like 5 or 10 seconds, right? How come it cools really fast in your mouth and not in the plate?
Well, the temperature difference between your mouth and the hot food is much different than that in the plate because in your mouth is like 98 degrees. So that's part of the reason. The amount of food as well in your mouth versus on the plate is different. So that's another reason. So like, if you remember in chemistry, they did those temperature equilibrium things. It's like the change in temperature. So since it's cooler outside your mouth than it is in your mouth, obviously it has a larger temperature change, which means it's going to change more quickly.
It's the difference between your the temperature of your skin rather than on top of your skin rather than temperature within your skin, basically.
Right, yeah.
You don't feel it so much.
Right.
There's less food.
Does that answer your question enough?
Yes.
Okay. All right. Any more blue cards? I can't see skyward. There we go. Okay. Other types of energy transferring. We have mechanical waves. So this would be like sound waves are considered mechanical waves. Sound is just a pressure wave of air, which is why you can't scream in space. I mean, you can scream all you want, but no one's going to hear you because the air molecules are so far apart that it takes them such a long time to hit another one and then move and hit another one. It's not really much pressure. There's not really any way for it to carry.
So they're technically air molecules in space. They're just too far apart.
They're really far apart because it's a vacuum. Because it's like the void, and they gravitationally attracted to things. So one molecule out in space has probably got enough gravitational force on it to kind of pull it into a planet. So there's not going to be a lot of molecules out there, but there is molecules out there. I mean, you see nebulas and stuff. They're out there. They're just really, really far apart from each other.
I think nobody got you.
You got me?
No,
So you're saying like the conch out in Star Trek is beyond unrealistic?
The what?
In Star Trek 2. Pretty good, and it echoes throughout like the galaxy.
Oh yeah, I think they heard it. Maybe if it was like transmitted through like radio waves or electromagnetic waves some way, and then picked up on like the way your radio works, then maybe. You just have to transfer his mechanical sound into some sort of radio recording station.
I was thinking like a mighty enough sound that still would be able to carry through space.
Unless it like launched that particles with it, so that if you like blew up the air force of the screen, and the parts from the ship carried that sound energy.
I still don't think there would be enough.
Can you make
That's
them
not up here.
sound loud enough to be heard on the other side of the world?
Yeah.
Yeah.
That's actually you just need the right microphone.
Yeah. Well, even like when it goes through goes through the atmosphere, you can hear that for a
Or you could dig a hole through the core and then shout through it.
No. Oh, right.
I think nobody can hear you scream in space. I don't think anyone got your obvious Battlestar Galactica reference.
That was aliens.
It was aliens.
Yeah. That's the point.
All right, so mechanical waves, sound, water, and seismic, earthquakes, they are mechanical waves. They actually transfer energy. They actually transfer lots of energy. Those earthquakes, a lot of energy. Electrical transmission, this is electric currents. These are basically moving electrons along. This is how energy enters electronic devices, moves those electrons. Okay, O'Brien, are you finished with your cup?
Oh.
Thank you. All right, transferring energy. Electromagnetic radiation. This would be light, microwaves, radio waves. Your microwave is actually named poorly because it omits microwaves. So it's more like a microwave emitter, not just a microwave. Or I like to call it a water resonator. My husband hates me sometimes.
Emitter or omitter?
Emitter. Emitter. I think I did.
It's microwaves.
Microwaves are not allowed.
They're the only thing that isn't in there.
It's everything but the microwave.
All right. So things that emit electromagnetic radiation, your microwave oven or your water resonator, and light traveling. X-rays. Mm-hmm. Yep. X-rays, gamma rays, radio waves, infrared, all of it.
Anything on the spectrum.
Anything on the spectrum. Radio waves are not sound waves. Mr. O'Donnell was trying to explain it to someone, and he's like, and sound waves are way over here, gamma waves are over here. I'm like, what? Radio waves, radio waves. Radio and sound, different.
You think politicians know everything about science?
Oh, yes, sure.
Yeah.
Sure.
Including that one congressman who said that we're going to run out of wind energy one day.
Oh.
Yeah, because when
As soon as we run out of sun energy, that'll happen.
Yeah, see, the thing is that once we use all the wind energy, the wind's going to stop.
Cracking on.
It's going to stop.
Yeah, a senator from Illinois said that.
Oh, my.
We're going to be cracking on it around something now. We're going to miss our deadline. You know how hard it's going to be?
All right, I see 2 red cups. Are we finished? I mean, I still have to do some problems here.
Oh.
I mean, I know I like to answer your questions because I love to talk about Earth science, but Earth and space science is my favorite. My husband was bothering me the other day about, I said the class is called Earth Space Science. He's like, well, there's nothing else. It should just be like everything science. Because it's like space and there's like the Earth, there's nothing else. I'm like, yeah, but it's science about the Earth and science about space. And he's like, but that's the entire universe.
He's technically correct.
I know he is. I'm like, but that's not what it's about. Okay, so when you're conserving energy, energy cannot be created or destroyed. It always has to either be transferred or it's either transferred in or out of the system or transferred into some other form of energy. It's not ever lost. But sometimes we'll talk about energy being lost, meaning it's transferred out of the system. It's not destroyed, it's just relocated. So sometimes I use lost. It just means it's not in our system anymore. So for us, our universe is just that system. So for us, it's lost. Okay, so here's our clicker questions. We have 80,000 kilogram airliner. It's flying at 900 kilometers an hour at a height of 10 kilometers. What is its total energy, both kinetic and potential, if the total was 0 when the airliner was at rest on the ground? So let's draw a picture. You can see my terrible airplane. There we go. Airplane.
Picasso.
There you go. Kind of looks like a shark, a little bit. Or like a sub sandwich with lettuce sticking out on the
like
side.
a Sharknado? There.
Sharknado.
Like sharks who work for NADU.
Okay, so we have a mass of 80,000 kilograms. It is flying at 900 kilometers an hour. Kilometers an hour. And initially, when it was on the ground, it was not moving, so it had no kinetic, and it was on the ground, so it had no potential. So at this point, it has both potential energy due to gravitation and kinetic energy. So its total energy, just at this point in the sky, what is its total energy at this point in the sky is going to be something like mgh plus 1/2 mv squared. Remember that you want to make sure this is in meters per second, so you're going to have to do a conversion here. 1 kilometer, 1,000 meters, and 1 hour, 3,600 seconds. And then plug in and solve. Oh, also this height of 10 kilometers, 1 kilometer, 1,000 meters. There you go. And so, let me start just. It does say megajoules. That capital M is mega, stands for 10 to the 6th. Yeah, that's why it's 10 to the 6th mega. Kind of makes sense that how much destruction occurs when it hits the ground, right? So it has that much energy, and then when it falls and hits the ground, that's how much energy it has to dissipate. So plane crashes are just like giant explosions and all this mess.
How many sections are in this chapter?
7. Okay, there's 7. We've got a lab for the next 4 days. Next Thursday, we're going to do 5.6/7, which is just power. And then we'll do the review and the test. The test is the 21st. Everybody has answered.
Why didn't we move back to the lab? Why didn't we move back to lab?
No, it's a different lab. A lab that you'll start tomorrow. Yeah, you gotta. If you haven't sent me your lab, you need to do that. It's late.
I don't have any information.
All right, so we should have gotten D, 10,300 megajoules. Very, very high. Question 2. A 15-kilogram crate initially at rest slides down a ramp 2 meters long and an incline at an angle of 20 degrees with the horizontal. If there's no friction between the ramp and the surface in the crate, ramp surface and the crate. What is the kinetic energy of the crate at the bottom of the ramp? These are very common questions. So they've given you that the crate is 15 kilograms, the angle is 20 degrees, and it is 2 meters long. This is the hypotenuse. You need to know the height, which would be the opposite of your angle. So looking at SOHCAHTOA,
Sine.
what do you want?
You want sine 20?
Yeah. So sine, theta, opposite over hypotenuse. To get the height, and then your energy is gravitational potential energy, right? Because it's initially at rest, and it's at the top of the incline. So you're going to go energy equals mg each. Cool. Look at that.
Should we intervene
Here, sorry. Should work now.
Which should be in degrees, right?
Say it again.
Why do you use that one?
Why do I use sine?
Oh, that's great.
Oh, mgh. It's at a height above where it's going to land, so it only has gravitational potential energy because it goes from here to here. It doesn't matter that it slides down the ramp. It could be going straight down, or it could go sideways, or it can go this way and then down. We're only looking at the change from where it started to where it is. If there was friction, then the path would matter, but there's no friction here. Oh, sorry, it's looking for, what is the, and all the potential goes into kinetic, because the system is conserved. So basically, initial equals final here. So this will be initial, and final is kinetic. So mgh equals your final kinetic energy, which it's asking for. It's not asking for the velocity. If it was asking for the velocity, we'd change this into 1/2 mv squared.
I'm trying so, but it's giving me like 0.0003,
What?
which is sine.
Did you do 2 sine 20?
I tried that one.
Let me see.
What math class you in?
2 sine.
So today I got
Let's-
the wrong. I started getting the
Oh,
wrong
never
answer
mind.
because mine's in radiant.
I guess I must have entered in
I was just like,
That's on my head. So it should be.
Are we supposed to convert kilograms to regular?
No, that's not what
no.
You.
Okay, see, that's what I did.
Oh, it's in kilograms. No converting.
Wait, but when the okay, so if the object was just dropping, right? That's kinetic energy. But since it's going down an inclined plane, wouldn't it travel a larger distance than the height?
Nope. I mean, it does travel a larger difference, but its potential energy hasn't changed.
Okay. Wait, but it's asking for kinetic.
Right, and
Yes.
it starts with potential energy and it ends with kinetic because it's at the ground.
But the energy is the same throughout.
Well, not necessarily.
Oh.
It is in this case because there's no friction.
Okay.
Get the total energy.
no friction.
All right, so the correct answer was 100 joules. All right, question 3. The same box Is it the same box?
No,
No.
the lighter box.
That's a different box.
They took everything out.
For some reason, it's a different box. Sliding down a different ramp with a different angle. So a 10 kilogram box starts at rest, slides down 3.5 meter ramp that has an angle of 10 degrees with the horizontal. If there's no friction, so again, energy initial is going to equal energy final. Find the velocity at the bottom.
This is the velocity this time.
So it's up here. Starts at potential, gravitational. It hits the bottom. All of that potential has turned into kinetic, so potential equals kinetic. And the equation for kinetic is 1/2 mv squared.
1/2 mv squared.
So it's going to be pretty much the same thing that you did here, except for different numbers. This is a 10, and this is a 10, and this is a 3.5. And this is now 1/2 mv squared. So if you look at that, m's disappeared. And you could solve for v. I need to throw my calculator. Awfully harsh on that calculator. Just because it gave you an answer you didn't like.
Is that working?
Yeah, no.
Yeah.
When they tell you the length of the ramp, how do you know they're talking about the hypotenuse and not?
Otherwise, they would tell you the height of the ramp.
What about the bottom?
They would never tell you the bottom part.
But as they were saying, the distance the ramp covers is.
Yeah, it never says that.
It could.
It doesn't.
That way.
Well, they could if they were like old FCAT where it's trying to throw you off or anything.
But, as far as I have seen, and I have taught physics for 4 years, not ever seen that. I mean, if it wanted to specifically say that, it'd be like the x distance the box covered. It would have to specifically say the horizontal distance. But whenever it says the ramp length, it means the hypotenuse. And that's a good question, though, because it's legitimate.
So 1/2 mv equals the potential energy, right?
1/2 mv squared.
Kinetic.
Is equals the
Kinetic.
potential energy.
Kinetic.
Oh.
Because it's got a v in it, right? Movement.
Yeah.
V for velocity. Potential is the height, gravitational potential. So it's got the g in it, gravitation.
Why are you putting your cup into your ears? What is that in your hearing? If most of those have holes through them?
Why would you ever have this kind
No, really? Does it improve your hearing though? This. But it says make everything sound really awesome.
Yeah.
Is that hearing thing? Is it still here? Does that improve your hearing?
No, this actually doesn't
I don't
improve
think
your
so.
hearing.
'Cause- okay, like the way hearing aids work is it's like an amplifier, just like a speaker, basically. So it takes in pressure waves and it converts them into bigger pressure waves with the electricity that it runs on the little battery, so that it has bigger waves in your ear. Your ear is made up of these like little tiny nerves, and the pressure wave that hits your eardrum. It's an ear drum, like it makes a, that works just like a drum, and it creates pressure waves into this gel in your ear, and that's how you've got balance and everything too. And so that gel transmits the pressure wave to the little tiny nerves. So the louder you listen to your music, the deader those nerves get. They actually start to, they're very, very sensitive, and if you listen to it really loud, they actually start to die on the ends, and they never grow back. So once you lose that hearing, you can't get it back. I mean, like a little bit, but not really. So whenever you mow the lawn, you should be wearing ear protection. Whenever you're in the garage or on the shop, whenever you put the earbuds in your ears, you should make it just loud enough so that you can hear it and not super loud, because if you hurt those nerve endings in your ear, they're not going to grow back. You're going to be one of those old people that's going, whack.
What?
Eh?
See? Like O'Brien.
But like, wouldn't a hearing aid that make your hearing less?
Well, I mean, a hearing aid you put in after you already can't hear things, so it's just amplifying the waves enough so that those nerves can, because they basically like receded in your ear, into the ear to protect themselves, and they never come back. So that you need a louder wave in order to reach them. They have to make it through not only the gel but also the thickness of your ear. We'll go through a whole thing in sound as well. I'll show you pictures of ears and stuff. It's gross. But I have vertigo, so yeah, everyone has now. I have vertigo, so I know a lot about the ear because of that. All right, so correct answer was 3.5, which most everybody got it. Sounds like the back corner got it. Or it's got ants in their pants. We're not really sure. All right, question 4.
Maybe they were.
A baseball catcher. Does anybody here even know what a baseball is?
It's a hard ball.
Sports ball.
It's like the white one, right?
It's sports ball, right?
Those small and soft, like this.
One that you hit with the bent
Baseball's
stick.
The one that
Yeah.
is made of pigskin that people throw.
All right, a baseball catcher puts on an exposition by catching a 0.15 kilogram ball dropped from a helicopter at a height of 101 meters. What's the speed of the ball just before it hits the catcher's glove at 1 meter above the ground? Ignore air resistance, even though that would be unlikely. So what kind of energy does it start with?
Potential.
And what kind of energy does it end with?
Kinetic, well, potential.
Kinetic.
Well, I mean, technically when it stops, it has potential.
Kinetic.
Is it just messing with us and we don't really need to include the 101? It should just be 100?
Yeah, because you're just looking at the change in the height. So if you really wanted to do it like if you said the ground was 0, this would have potential, and then by the time it goes 1 meter, it would have a little bit of potential and kinetic. But you could just say that he catches it, and you could set that as 0, and the change in is still going to be the same. So I would say that he catches it at 0 and just start it at 100.
Okay.
The rounding is actually not as big, so
Yeah, it wouldn't change your answer.
It's gonna hurt.
Yeah, it is.
Heck yeah.
What's the answer? It's gonna hurt. I guess baseball catchers don't have a lot to do, huh?
People don't realize 2.2 meters per second is super fast.
Yeah, it is.
Highway speeds,
That's like,
50-some miles an hour.
yeah, like 90 miles an hour is like 28 meters per second or something like that.
That's my game on aerospace program. Like, you drive a car and you're outraged that can't go full turn at 20 meters per second. And then you don't realize how fast that really is.
Yeah.
Why can't they turn on a dime at 50 miles an hour?
Yeah, well, and when you don't feel it either when you're on the simulators and stuff, it doesn't seem like they're going that fast. You don't feel that acceleration. Because you can't feel velocity. It's such a nice thing in physics. It's just like everything comes down to energy. You can do everything in energy, I feel like. And you can break it down into like chemistry. The reason things go from one thing to the other is energy, basically. In biology, the reason that life exists is energy. It's all about transferring energy. I said chemistry.
Yeah, well, no, not biology. Biology, you just said physics because you try to take the credit for everything as a physicist.
No, I like energy in general. It's very universal. You can use it across all situations, all the sciences. So deep.
Right, so what equation would we use for this one?
What kind of energy does it start with?
Potential, yes.
mgh.
Right?
What kind of energy does it end with?
Oh. Okay, so that would be do that. Oh.
Basically what we did for the last question.
Yep. I like to hear that.
What's the speed of light again?
3 times 10 to the 8 meters per second. It's fast. Wouldn't it be nice if all the answers were like that? It's like, it hurts. It's fast.
Yeah.
That's pretty much like what Physics 1 is.
Goes faster, not as fast.
Right.
It hurts slightly less.
It hurts slightly more.
That's one thing I don't like about the conceptual physics book.
I
is all the
don't
answers
survive
are like
the
that.
impact. I do survive the impact.
I'm such a math person too. So. Do you need more time, or are you good?
I'm good.
Okay.
Good afternoon, parties. Good afternoon, announcements. Any senior or junior who is not in ROTC and wishes to sign up for the